Hi, and welcome to the second session of the Basic Stats course. This session will cover confidence intervals, hypothesis testing, and p-values. My name is Martha Elwensberg, and I'm a quantitative researcher at NIHR ARC West. These are the learning objectives of this second session, so hopefully by the end of this lecture, you will have a better understanding of the following. So that's what it means to infer from samples to populations. You will understand what sampling variation means, the difference between precision and accuracy, why we need standard error, what it means, and how we can use it to calculate confidence intervals, and finally, when you will use hypothesis testing and how to interpret p-values. I will try to explain all these concepts that I showed you in the previous slide by using this example, which is not a real study, it's a fake example. So let's say we want to do a weight loss program and we want to know how effective this weight loss program is. So we recruit 100 women aged between 20 and 35 years old, and we measure their weight beforehand and after. And then we can calculate the mean weight loss after the intervention. So before, on average, they weighed 70 kilograms, afterwards 66.3 kilograms. So there is a difference in weight of 3.7 kilograms. So we can already see that on average, these women lost weight. And if we look at the graph that I'm showing here, so you can show the data like this as well, and you can see that the weight on average before is higher than after. But this is not enough information to judge whether this is a real effect and whether this is a significant reduction in weight. To judge that, we need either the p-value or confidence intervals. So here I'm showing the confidence interval and the p-value. So the 95% confidence interval goes from 3.4 to 4 kilograms. And how you read this is that you are 95% confident that the true weight loss, the true value of weight loss, is somewhere between 3.4 and 4 kilograms. So that means that even in the worst case scenario, you expect that the weight loss program causes at least, or on average, a 3.4 kilogram weight loss, which is a good effect. So this is what you would want to see. And if we look at the p-value, it's very low, so this means that it's highly significant. So this is an example of a real study of a paper that was published in The Lancet in 2013. And this shows the results of a randomized controlled trial where they looked at the effectiveness of using electronic cigarettes for smoking cessation. And they compared three groups. So they had one group where they used e-cigarettes that contained nicotine, one group e-cigarettes without nicotine, so that was the placebo group. And then they also looked at compared the effect with using nicotine patches. And here I just show you a part of the results. So this is how results like these are presented in papers. So they say that most participants relapse within 30 days after stopping smoking. But there's a difference, they found a difference in the different groups. So the people using the nicotine e-cigarettes, their time to relapse was 35 days, and then they show this confidence interval. And then because they compare it to a different group, and this is the one that uses the patches, they again show the results. So this is their estimate for this group, and followed by the confidence interval and the p-value. So this p-value shows what the difference is between the first group and the second group. And then they also compare this to the placebo e-cigarette group, and again they show you the estimate and the confidence interval and the p-value. So we will come back to this paper at the end of this session, and then hopefully these concepts make more sense to you. Okay, so what does it mean to infer from samples to populations? So every time you do a study, you're interested in a certain population. You want to know something about a population. But because it's hardly ever possible to measure everyone in a population, you need to take a subsample. So what you do is if this is the population you're interested in, you will recruit a sample from this population that is supposed to be representative of that population, and you will do your measurements in this group. So this can be a mean, median, proportions, or percentages, whatever you want to measure. But of course, what you're really interested in is, what does this tell me about the population? You're not interested in the sample per se, but you want to say something about the population. And that's what we mean with statistical inference. So to do this, you will use standard error, confidence intervals, and p-values, because they tell you how likely is it that what I see is a true effect. How likely is it to see something by chance, and how likely is it that it is a true effect. So here are just some examples of when you would use statistical inference. So the simplest example is just to estimate population demographics, such as what is the percentage of smokers in the UK. So you come up with an estimate, which is in a percentage in this case, and you can draw a confidence interval around that. And also for comparing groups, so in the weight loss study example that I've used before, we had a before and after measurement, and you will measure the difference between before and after and look at the confidence around the difference. Or you can compare two different treatment groups. So this is, for instance, the e-cigarette study that I mentioned. So when you compare e-cigarettes to placebo e-cigarettes, or another example would be statins versus a placebo. And in this case, they measure a mean difference and show a confidence interval there. And finally, you can also have studies that compare one treatment to another treatment. So this was also an example in this study of e-cigarettes, where they compared e-cigarettes with nicotine patches. Or another example would be paracetamol compared with ibuprofen, where they could measure pain scores, and even around these scores that do not have any units, you can draw a confidence interval. So what does this mean for the weight loss example that I've mentioned? So in the weight loss example, the population that we're interested in are women in the UK between 20 and 35. So that's why we've recruited a sample of women between 20 and 35 that live in the UK. And our outcome in this study would be the mean weight loss in kilograms after the intervention. And what we want to know is, we want to estimate the true weight loss of the population. So this is statistical inference. And we want to know, whatever we've measured in our sample, could this have been a chance finding? And how likely is it to see this effect if actually the weight loss program is ineffective? So whenever we do a study, we take a subset. And because we take a subset, we won't measure the exact truth, because we haven't measured everyone. And we can also imagine that it will never be the exact same value as if we would have measured everyone. So if we repeat the study in exactly the same way, we recruit people in exactly the same way, we will still get different people in our sample. So we can imagine that the answer will also be slightly different. You would expect them to be similar, but every time they will be slightly different. So how do you know how confident you can be in your estimate, and which of these studies is close to the truth? So that's when we want to calculate things like confidence intervals and p-values. So this fact that every time you take a sample and you get a different estimate, that's called sampling variation or sampling error. So if you have performed a study and you have calculated a sample mean, you want to know how good this sample mean is as an estimate of the population mean, because you ultimately want to know the population mean. So a good estimate means that it's both precise and accurate. And these are very much related concepts, but they're slightly different. And I think these 4 bullseye show nicely what the difference is. So you can have an estimate which is precise but inaccurate. So in that case, the errors are all very close together, or your measurements are all very close together, but they're not close to the truth. So the bullseye represents the truth. You can also have a situation where your measurements are not very precise, but they are accurate. So here the errors are all are all on average close to the truth, so the bullseye, but they are not close together. And then of course you have situations where your estimate is not precise and not accurate, so they're just all over the place. And ideally you have an estimate that's both precise and accurate. So precision means errors are close together, and accuracy means it's close to the truth. So this is just another way to look at what the difference is between precision and accuracy. So if the red line shows the distribution of the population, so this is the truth. This is something you don't know, so this is in case you were able to measure everyone in a population, then you know what the true underlying distribution is. The blue bars are all the studies that have tried to measure this, and some studies are very close to the truth and other studies are further off. So on average, these studies, if you would take the average of all these studies, you would think that the true value is around here, although the true value is actually here. So the difference between these things, that's what we call accuracy. But precision is how wide this distribution looks like. So if the studies would be very similar, then you would be much more confident about this estimate of the mean. But this is quite a wide range in studies, so some studies thought the effect was all the way here, and others thought it was all the way here. And we can only calculate precision, we cannot calculate accuracy. And we calculate precision by calculating the standard error. And the higher your standard error, the lower your precision. So you want to have a low standard error to have a high precision. And there's two things you can do to influence precision or your standard error. And that's either by changing the sample size. So the more people you have in your study, the more precise your estimate will be. And on the other hand, the lower the standard deviation of your variable that you're measuring, the higher the precision. So this is what the formula looks like for standard error. So again, standard error is a measure of precision. So you can, and as I mentioned in the previous slide, either you change the standard deviation, which is not that straightforward, or you change the sample size to have an effect on precision of your estimate. So the higher the standard deviation, the higher the standard error, and the higher the sample size, the lower the standard error. So again, let's go back to our weight loss example. So what does this mean for the results that we had from our weight loss study? So we had 100 people in our study, and we had their before measurements, after measurements, and the difference. And I'll just give you the standard deviation. So if standard deviation is a 1.5, how do you calculate the standard error? So we need to divide the standard deviation by the square root of the number of participants in the study. So that was 100. So that means that the standard error for this study would be 0.15. So I've showed you how to calculate the standard error, but what's the point of doing this? Because you can hardly ever see it reported in papers. But what you do see is confidence intervals, and you need the standard error to calculate the confidence intervals. So now you know what goes into the standard error. It's dependent on the standard deviation and the size of your sample. So how do we get from there to the confidence intervals? Well, to explain this, we have to do a thought experiment first. So let's assume that we have all the resources in the world, and we can repeat our study 1,000 times. So 1,000 times, we, in this case, we take a sample of 20 women to do our weight loss program, and we calculate the effect, and we do it again and again and again, and we do that 1,000 times. So here we can then show all our results. So instead of having a measurement per participant, we have a measurement per study. So these are all the mean values per study, so the results of each study in weight loss. And we can show the same data as we would show individual data as a distribution. And as you can see, that this also forms a normal distribution. But again, here we're showing sample means, so these are all different studies. So most studies found something like a 2.5 kilogram weight loss, and there are some outliers, so some studies found more than 5 kilogram weight loss, others found no weight loss, or some even found an increase in weight because it was lower than 0. The weight loss was negative, so that means an increase in weight. And in the first session, you've learned that the normal distribution has a few characteristics, and these same characteristics apply for our normal distribution that I just showed of our sample means. So just to compare, when you draw a normal distribution, or when you look at your data from one study and you just show all the individual values, then you can get a normal distribution if this is a variable that's normally distributed. And you've learned in the last session that 95% of these values will fall within about 2 standard deviations on either side of the mean. So you've calculated the mean of your study, and by definition, if these are normally distributed, 95% of the individual measurements will fall somewhere between 2 standard deviations on either side of the mean. And you can apply these same rules to the distribution that I've showed you on the previous slide. So if we're talking about the distribution of sample means, so again, these are not individual studies, but it is not one individual study, but these are like 1,000 studies that we've done over and over again. So in this case, you can calculate the mean of these studies, of the study results. So the 0 here represents the mean of the means. And then the same rules apply, that 95% of the study means will fall anywhere between -2 and +2 standard error, in this case, of the mean of means. And that 95%, that's where our 95% confidence interval comes from. So if we look at our study, so the one that I've showed you in the beginning where we said that there was a 3.7 kilogram weight loss, so our study would have been somewhere here. And of course, I said this is a hypothetical example to do a study 1,000 times, because you will never be able to do that. So you don't actually know that your study is, or where your study is in this underlying distribution, if you would have done the study 1,000 times. So that's why you draw a confidence interval, because your confidence interval says that you're 95% confident that the true value, so that would be here, the true mean, falls within the confidence interval that you draw around your measured mean. So let's look at this graph again. Just take the pointer. So if we look at the graph on the right, so if our study is about here, then if we draw this confidence interval, so I told you the confidence interval is calculated by using the standard error, and the standard error is dependent on the standard deviation and the size of your population, or the size of your sample. So if this is our study mean, then we try to estimate the underlying standard error of the population by using the standard deviation from our study and the sample size of our study. And then we calculate the standard error. From there, we estimate the confidence interval. And as you can see, that because our study fell within this 95%, not too far from the true mean, our confidence interval will contain the true mean. But as you can also see from this picture, that in 5% of the cases, so these are the outlier studies, if your study is an outlier, and of course you will not know this, so let's look at that. So if this is your study, and this is the mean that you have measured here, and you draw your confidence interval around it, the true mean does not fall within your confidence interval. So this is a decision that you take as a statistician. You decide that you are happy with a 95% confidence, and that immediately means that this means that there's a 95% chance that the true mean falls within this interval, but there's also a 5% chance that the true mean doesn't fall within your confidence interval. So this is another way to look at it. So if these are if you did one study 100 times, so these are 100 different, or 100 the same studies that you've repeated with a different sample, and every cross shows your estimate of the effect, and the true effect is shown by the blue line, so the true effect would be 5, then almost all studies, if they draw the confidence interval, I say almost all because it's about 95% of the studies, the line crosses the line of the truth. So in 95% of these studies, the truth lies within the confidence interval that they drew around their estimate. But the estimates, they are quite varied. So they can be close to the truth, or they can be further away from the truth. And you also see that there are a few studies where this is not the case. So these are your 5%. So these are, if you do 100 studies, about 5, in this case 6, but around 5 of them, the confidence interval will not hold the true mean. And I said that this is something that you can never do in real life, but in fact, this is what you try to do in systematic reviews and meta-analysis. So this is a forest plot showing different studies that were published and showing the effect estimates of each study plus their confidence intervals. And then from here you try to estimate, so this is the line of no effect, and you try to estimate the truth by combining all these studies, and hopefully the combined estimate will be closer to the truth than any of these single studies. So I've described how you theoretically get to a confidence interval, but this is the formula. So you need your sample mean, and you need your standard error to do the calculation. And then you get this range from almost 2 times standard error on either side of the mean. So how do we interpret this? So this is how you can read it. If you see a result like this presented in a paper, that we can be 95% certain that the true population lies within a 95% confidence interval for any given sample. So if the confidence interval is narrow, the sample estimate is precise, and if the confidence interval is wide, the sample estimate is imprecise. So going back to our weight loss program, let's see how we would calculate the confidence interval for the data that I've shown you so far. So the only thing we need is our estimate, so that's our weight difference 3.7, and we need the standard error. So we want to calculate two things. We want to calculate the lower end of the confidence interval and the higher end of the confidence interval. So that's why we'll do the sample mean minus 1.96 times the standard error and sample mean plus 1.96 times the standard error. So if we fill out the numbers, so that is our 3.7 weight difference and the standard error that we calculated before. And then we come to this confidence interval. So the confidence interval goes from 3.4 to 4.0. And your estimate will always lie exactly in between your higher and lower estimate. Okay, so this is the last part of this lecture, and it's about hypothesis testing. So for every statistical test, you will start by defining your null hypothesis. And your null hypothesis always states that there is actually no effect or there's no difference. So if you have seen a difference or an effect in your study, you're asking yourself, what is the chance that the observed difference or effect is actually due to sampling variation. So in our weight loss example, our null hypothesis would be the weight before and after the intervention is the same, or there is no effect of the intervention on weight. So after defining the null hypothesis, you can go ahead and do your statistical test. The next two sessions will dive deeper into how to do these tests. So we will skip that part for now and just assume we've done a statistical test which gives us a p-value. So what do these p-values mean and how do we interpret them? So if we have a p-value of 0.001, you interpret this as follows. There is a 1 in 1000 probability that the mean difference observed arose by chance, i.e. sampling variation. Or that the probability that you would observe this estimate given the null hypothesis, so that means assuming that the null hypothesis is true, is 0.001. So that means it's very unlikely to see the effect that you've observed just by chance. And that's why if the p-value is very low, we say it's highly significant, and we assume that what we see is true, is a true effect and not caused by chance. Or in another example, if your p-value is 0.1, then it means that there is a 1 in 10 probability that the mean difference observed arose by chance or sampling variation, or that the probability that you would observe your estimate given the null hypothesis is 0.1. Okay, so the p-value says something about the likelihood of finding a difference if in fact the null hypothesis is true. And the null hypothesis always says that there is no effect. So if we assume the null hypothesis is true, we can also draw again a distribution of sample means. So this is if we do the same study 1,000 times on different samples from the same population. So we would expect that most of those studies find something close to the truth. So they will all vary around the true value. And the true value is 0 because there's no weight loss, because we assume that our weight loss program is ineffective. We would also assume that some studies find a small difference. So some studies might find that there is some weight loss, and other studies might find that the people have actually gained weight after doing the program. So this can all be explained with sampling variation. Now what a statistical test does is it looks at how many standard errors your estimate in the study that you've done, how many standard errors it is removed from the value of no effect. So in this case, the value of no effect is 0. And in our weight loss example, we measured an effect of 3.7 kilogram weight loss. And we also measured that the standard error was 0.15. So if you calculate how many standard errors our estimate is removed from 0, that's actually quite a lot. So that's more than 30 standard errors we are removed. So measuring something that's 30 standard errors removed from no effect, the chance of finding that, if this is true, is really small. And that's why we got a very small p-value. So p-value that was less than 0.001. So the p-value gives you the strength of evidence against the null hypothesis. So the smaller the p-value, the stronger the evidence against the null hypothesis. So you should see it as a grayscale. And if you have a very small p-value, like in our weight loss example, so that means that there's strong evidence against the null hypothesis. It means it's just really unlikely that the null hypothesis is true, and the smaller the p-value, the more unlikely it is that the null hypothesis is true. So let's look back at our weight loss example. So I already mentioned what we saw in the beginning, that we had a very, very small p-value. So we have found strong evidence that there is in fact a weight loss and that there is a significant weight loss in our study. So now we have covered all these objectives. So we've talked about inferring from samples to populations, and we've discussed sampling variation, the difference between precision and accuracy, the standard error and how you need it to get to a confidence interval, how you arrive to a confidence interval, and how to do hypothesis testing and how to interpret p-values. So just to summarize, if these are our results and you would write this in a paper, this is how you would describe these results: that we are 95% confident that the true effect of the intervention is weight loss between 3.4 and 4 kilograms. And the probability that the observed difference arose by chance, i.e. sampling variation, is less than 1 in 1,000. So that's what the p-value shows us. So, and finally, just to show you again the paper that we saw in the beginning about the electronic cigarettes for smoking cessation. So hopefully these results are now easier to interpret. So you see their estimate in days with the confidence interval. So actually they think that the median time to relapse for people that use nicotine e-cigarettes can be anywhere between 15 and 56 days. And for the group that used the nicotine patches, they believe that the true number of days to relapse is anywhere between 8 and 18 days. And for the placebo group, this was anywhere between 5 and 34 days. So hopefully after this lecture, it will be easier to read papers like this and interpret findings where they talk about confidence intervals and p-values. And well, thank you for listening.